Hello, welcome everyone to another session of the M.Ed Social Science Data Lab. My name is Dennis Cohen and I'm happy to welcome you to today's workshop by Malte, Grönemann and Oke Bahnsen. The Social Science Data Lab, as you know, is an event series here at the Mannheim Center for European Social Research, where we provide a platform for tools and methods for the collection, management, analysis, and visualization of data in the social sciences. In the current fall 2022 semester, it is co-organized by Ruben Bach, who's also here today, and myself, with the support of our student assistant, Andreas Küpfer. To briefly introduce our speakers here today, of whom you can see only one, we have Malte here. He's a PhD candidate and research associate in sociology here at the University of Mannheim, and his work focuses on complex social systems and quantitative research methodology. Our second presenter is Oke, who is also a PhD candidate and research associate in political science at the University of Mannheim, whose work focuses on coalition politics and electoral behavior. Unfortunately, Oke cannot join us in person here today, neither can he join us online, but he has kindly agreed to pre-record his part of the talk, so we will play a video recording for you. Now, in their talk today, Malte and Oke will give an introduction to the toolbox that is agent-based modeling, featuring applications to social scientific research with specific applied examples from Malte's work in sociology and Oke's work in political science. A quick disclaimer for everyone online and on-site here today. We are recording today's session with the intent of putting that up to our YouTube channel in a couple of days or weeks. We are recording it in active speaker mode, which means if you, people joining us online, ask questions via audio, your audio will be recorded, and if your camera is on, so will be your video. If you want to avoid that, feel free to post your questions in the chat, in which case I will read them out for you. Okay, that being said, Malte, thank you so much for being here today. Thanks also to Oke, who cannot be with us here today, and the floor is yours.
Yes, thank you so much. Thank you for the great opportunity to give a little bit of an introductory talk on agent-based modeling, which is a toolbox that has gained some popularity in the social sciences already, but only within a few subdisciplines. So it might be the case that you still haven't heard of it, but some of you might have. All right, we're going to cover three things in total. The first thing is, well, what actually are ABMs? So what is this that we're talking about? Second, why is it relevant or useful in the social sciences specifically? And then we will show some examples. And Dennis also already said it. I will present work of mine on simple and complex contagions. And my PhD topic actually, which is the social economic model of the housing market. And Oke will present his PhD or part of his PhD, which is a dynamic model of multi-party competition. And then we'll have a little summary and some recommended literature if you want to dive deeper. So first of all, what are agent-based models? First of all, what even is a model? Modeling is a simplified a model is a simplified representation of social reality, in our case, since we're in the social sciences, that serves to express as clearly as possible the way in which one believes that reality operates. So it's a simplification of reality for analytical purposes. And every one of us is a modeler in every instance. And this is very well expressed in a quote, which is actually one of my favorite quotes by Donella Meadows. Everything we think we know about the world is a model. Every word and every language is a model. All maps and statistics, books and databases, equations and computer programs are models. None of these is or ever will be the real world. But then the question is, do we model implicitly? So like as normal humans, we always have like a made-up copy of the world in our head. Or do we model explicitly? And this is what we're going to talk about today. We're using models explicitly as a tool to understand social reality. And explicitly modeling This can also be done via language, but formally modeling has some advantages, especially for scientific research. Some of them are the clarity of assumptions and the deductions that we can infer from these assumptions. We have a much higher precision usually if we have formal models. And oftentimes, especially in the social sciences, we have outcomes from our assumptions that we are not able to grasp just by thinking about them. So we need some way, some calculus of obtaining the results from our assumptions, which might be unimaginable or unintended in some way. Agent-based models are, of course, a specific type of model and specifically a computational model. So agent-based models are a computer program that is designed to formally represent a set of hypotheses and executed to deduce in a numerical form the logical implications of such hypotheses. The computer program is of a particular kind, however, and this particular kind is that it's agent-based. Agent-based means that we have a bottom-up perspective on modeling phenomena. How this is done, we will see in a second. So we have a computer program that we feed some assumptions into, some hypotheses, and then use it as a means to obtain macro-level predictions or phenomena. This is already hinting us at that this is not necessarily, or in most cases, not an empirical method. Quite different from what this talk series usually is about. This is not necessarily about empirical data, but this is artificial data produced by pre-specified assumptions. You can implement empirical data with ABMs and use connections between these two. Oke will show an example how you can use empirical data with agent-based models. However, most agent-based models currently will be purely theoretical. So if you read in papers. The basic assumptions that make agent-based model a specific kind of computational modeling is that agents are autonomous, that agents are interdependent, that agents are adaptive and backward-looking, which gives us the opportunity to model memory and learning, and they can be heterogeneous in their attributes. So we have agent, and they perceive their environment and or the other actors, and they interact with this environment and the other actors. They have so-called condition-action rules. So if a certain condition is specified, if this is true, do this or that. And because the other agents are interacting with other agents, an action of one can lead to a cascade of actions through the entire model. Quick review of other types of models to draw a little bit of a distinction of this type of modeling to maybe more well-known approaches. The first one are structural equation models. You're all familiar with structural equations. The most common example are regression models, of course. Those are models based on data, and there you model a relationship between variables, attributes of some observations, and not relations between agents specifically, but the acting entities that we want to study. So we have like a somewhat of a disconnect between our empirical study, which is about variables, and our theoretical inquiry, which is about people, organizations, political parties, whatever. Difference or differential equations are probably the most common mathematical models, also in the social sciences, but of course, especially in the natural sciences, they're quite prevalent. There we can use calculus to derive solutions. Problem is, in many social science applications, this is relatively hard to come up with a differential equation. And if you can, those likely will have no analytical solution. Microsimulation is another form of computational simulation that's used in the social sciences. They are more about prediction, and there the actors or agents are not interdependent. So you just track changes in their attributes over time, and you have specified rules of how they evolve. But they evolve basically isolated from each other. Cellular automata, you might be familiar with those. One very famous example is Conway's Game of Life. In some sense, cellular automata are a specific subset of agent-based models. Cellular automata are agent-based models where the individual agents do not move and the network doesn't change. So they have always the same agents with whom they interact. That's a cellular automaton. Whereas in agent-based modeling, we do not have this restriction that the agents with whom they interact stays the same. To summarize this is taken from Flache and Macy's book chapter in the Handbook of Analytical Sociology. Structural equations and system dynamic models, even with longitudinal data, are not sufficient because they tell us only about the interactions among the attributes of the actors, but not the actors themselves, who are typically assumed to be fully independent. Nor are game theoretic models sufficient because the Nash equilibrium only explains why a population pattern persists, but not how it obtains or changes. So we have an inherently dynamic and actor-centric view in agent-based models. The other modeling frameworks are fine, they're great, but they have their downsides and their upsides as agent-based models do for themselves. ABMs can be used in a quite different array of settings. And in ascending order of required empirical realism, first you got so-called toy models. So you have very abstract, very highly stylized, basically thought experiments. Yeah? You have a very abstract reality that's very simple, very reduced, and you change one or two things in a very stylized fashion and observe outcomes. Second is explanation, so using it as a tool for proper theory building of some generality. Again, these distinctions are very blurry, so it's a slippery slope. It's continuous, not discrete. You can also use agent-based modeling for causal inference or so-called in silico experiments, where you have a relatively high realism situation and compare different simulations based on different initial conditions. Oke is showing you how he implemented this. And of course, what probably most people think about when they hear the term modeling, you can do prediction. However, agent-based models usually are more concerned with theoretical development, especially in the social sciences, and not so much with predictions. Although they're used for prediction, especially in other substantive fields like geography or epidemiology. So they're more common to have much more realistic models that are also used for forecasting. For example, some of the COVID models that policy decisions were based on are likely to be agent-based models. Many of them are probably systems of differential equations, but some of them also would have been agent-based models. Simple models that have counterintuitive results are often more credible in that sense that they are explainable. If you have more realistic, more complex models, and you have a finding that somehow feels weird, you are not able to explain it that well why this happens. So the credibility of coming from other parties might be reduced in these cases. So it's a trade-off. ABMs and causal inference, as I said, Oke is going to present this in more detail. To have a little bit of an overview why this works, basically, we can compare it to randomized control trials and observational studies. In randomized control trials, we have our classical division between treatment and control. They get exposed, and then we observe the outcome of this exposure, In observational studies, we have a look at the naturally occurring exposition and try to isolate them and then compare them. And in simulation studies, we build a highly realistic model, and then we have one simulation given these conditions, and then another simulation, or to be exact, or many simulations, because since it's stochastic, you cannot rely on a single run of this model, and then compare the models or the model outcomes based on different initial conditions. Since it's a computational model, we of course need software to implement these models. And essentially, every programming language can be used for agent-based modeling, which is because almost all software languages these days support object-oriented programming. OOP is very similar to agent-based models in the way they're structured, because they can define classes of agents, so agents that have specific attributes, and then the specific agents with their specific attributes are objects. The most common software frameworks for agent-based models are NetLogo, which also has a graphical user interface, and is more like an ABM environment and not a general purpose programming language, which also has an interface to R. Java is quite popular using the Mason framework. There are two packages for Python that implement agent-based modeling quite easily, which are Mesa and Agentpy, and the new and uprising programming language for statistics and data science, Julia, also is suitable for agent-based models. All right. Questions so far? But what agent-based models are? None? Great. So now that we know what ABMs are, why are they useful for social science? Well, I've dug out an old quote by an old French guy, Émile Durkheim, one of the founding fathers of sociology. Society is not the mere sum of individuals, but the system formed by their association represents a specific reality which has its own characteristics. Undoubtedly, no collective entity can be produced if there are no individual consciousnesses. This is a necessary but not a sufficient condition. In addition, these consciousnesses must be associated and combined, but combined in a certain way. It is from this combination that social life arises, and consequently, it is this combination which explains it. By aggregating together, individuals give birth to a psychical individuality of a new kind. So Durkheim defines the social as an emergent property of individual action. So something that is produced by action in its interdependence. And this is actually one of the main reasons why Durkheim favored sociology as a distinct discipline and separated it from psychology, because it stated, well, it's not just that we can aggregate, that we can sum up individual behavior, but we need to understand how they relate. And James Coleman, another great of the discipline in sociology in this instant, has provided a scheme of how to think about this type of explanations that we typically need in the social sciences, which is the so-called Coleman board or micro-macro scheme. So we have a social observation phenomenon, and this is perceived by an actor that, based on their beliefs and his perceptions, acts accordingly. And this is aggregated to the macro level. And thereby, you have a new social situation, and the entire thing starts from before. And ABMs are a tool specifically designed to model this link from micro to macro. You pre-specify how agents perceive their surroundings and how they act given these conditions. And if you have some, or if you're interested in some emergent properties and some interactions of these agents, you can observe them by running this simulation, which is often very hard to do it by any other means. Just a quick survey. Do political scientists know about this scheme? You do. Something that I always wondered about. This is just like an isolated sociology thing, or. All right. So the interest in ABMs therefore reflects a growing interest in the possibility that human behavior may be complex meaning interacting, interdependent, in some way networked, nonlinear. So the relations and the interactions lead to tipping points, cascades, and nonlinear relationship, that they are task dependent. So task matters, also because agents are adaptive and backwards looking. Social phenomena are self-organizing. So the social is something that happens by itself. It's not top-down, regulated by some authority, but it emerges in itself. And most agent-based models are stochastic. Something that we are very bad at to grasp what the effect of stochasticity are if we only use language. So social complexity treats social dynamics as emergent properties of local interactions. So we study global macro phenomena based on local interactions among adaptive agents who influence one another in response to the influence they receive, which thereby often creates feedback loops and rolls out cascades of action. However, ABMs do not solve everything. Of course they don't. For any theoretical model, no matter how you specify them, you usually have multiple possible explanations or ways to go about them. So it's a sufficient, so it's a necessary but insufficient condition that your model can produce your macro outcome that you're interested in. Therefore, you need empirical hypothesis testing. And the second drawback, again, this is not specific to agent-based modeling. You have the trade-off between how realistic shall the model be and how traceable or the model is, or am I able to analyze and understand the outcomes of my model? So, and this will, of course, heavily depend on your research goal, right? If you do causal inference or prediction, you don't really care whether you understand everything that your model produces, as long as the predictions are good. If you want to have explanation, you really want to know why something happens. The most we can say is that ABC models, which is a synonym for ABM model, stands for agent-based computing models, can take us well beyond what we can know using discursive models, so language based on theoretical intuition, or statistical models of interactions among variables, or mathematical models of interactions in a static equilibrium. So we have a dynamic perspective for theoretical purposes. There are some fields that, or some substantive areas where ABMs are relatively commonly used already or have made some impact. In sociology, there are large portions of network science and network sociology in particular work with agent-based models. We have diffusion models of informations, innovations, or disease, as we know in the last 3 years. But also social influence, the emergence and change of institutions and social norms are examples where ABMs are quite influential already. Political science, you have, for example, opinion dynamics and polarization or party competition. And there is n-person games and evolutionary games theory, economics, stock market models, financial crises, and industrial networks and supply chains. In general, our subjective impression is that sociology is the discipline where agent-based models are most prominent character. So they're still relatively rare for the discipline as a whole, but relative to political science or economics, there's more research on agent-based or using agent-based models up to date. All right. If there are questions, I'm happy to take any. Otherwise, we would go for examples. Yes?
I don't know when to ask my question, maybe for the discussion part, but I wanted to know, in public policy or policy evaluations, like we hardly see, or it is very difficult to implement through randomized experiments. And as far as I understand this framework, this could be the tool for evaluating policies and their effects before they are implemented in large-scale reality and projects. Do you have any idea why this is not the case?
It is the case.
It is the case.
Quite frequently.
Okay.
Could you give some social science?
Okay.
As I mentioned in epidemiology, for example, in COVID cases, there will be agent-based models that for this specific purpose, testing out whether some social distancing measure or some policy change does have an effect, and quantifying this effect, whether it's reasonable with regard to a restriction to freedom. Another field that quite commonly uses agent-based models for prediction is geography, especially urban planning, traffic simulations, and testing how different traffic flows change, for example, pollution patterns, air pollution, something that people model. So this is done. But because we are thinking about the social sciences predominantly, there is less common still. But yeah, this is basically referring to this causal inference idea of agent-based model, right? So what happens if we implement that? No, this is a very fruitful approach indeed. All right. So the first example that I'm going to present to you is more of a toy model, or somewhere between a toy model and explanatory models. And this considers the information flow through networks. And specifically, you can have multiple sources, of course, for example, like media coverage. But what I'm interested in is that people tell each other some information, or forward them, or word of mouth type stuff. And we know that human networks are typically small world networks. Small world networks means that we have a very high community structure. So we have these, when you look at nodes close by each other, they are all linked. So here you can see this, like every node has ties to their 5 neighbors around them. So the next neighbor and the second order neighbor. But also we have a few so-called bridging ties. So these are the lines that cross through the entire network. So there are isolated long ties that connect different parts of the network and therefore provide a shortcut in that sense. This network structure means that information can propagate through these networks very, very rapidly. And this is an illustration taken from a book by Damon Santola. And you see here in 5 days, the entire, or 5 time steps, if you will, the entire network is propagated from only 2 people having this information on day 1. That's very, very fast. The second piece of background information is that there's an observation in sociology that for high-stake information, so we observe this rapid diffusion, but the more high stakes the information are, and especially for behavior, the diffusion speed is much slower than we would expect based on this network structure. And one possible explanation, which is forwarded by Santola, is that humans only believe some high-stake information if they have multiple sources of reinforcement. So if I have 2 independent contexts that tell me, yeah, this is actually true, or do this, or whatever. This, therefore, means that, first of all, the information spreads more slowly because it cannot go back. It can only, in fact, in the next step, this one, because this one is here connected to this one and this one, but all the others, they cannot be reached because there are no ties to 2 or more people that are already aware of this information. So this is the first thing, that it's slower overall. And the second thing is they cannot take advantage of these bridging ties because they're isolated ties bridging through the entire network. More importantly, the information can therefore be trapped in subnetworks if the bridges have not the sufficient width. So if you have a network like this, and Zephyra will never adopt this information simply because of the network structure. There are no 2 ties possible between people that have this information at this time point. So therefore, the information can spread around the network here. So there one connection, there's another, so this one can get infected, then so on. But here, it doesn't work because the width of the bridge is not far enough, not wide enough. And what I study is how forgetting, and in another part of the paper also remembering, affects these diffusion processes. So if people forget the information, how does this change equilibria and the overall pattern of the diffusion? And this usually, or first of all, means that not the entire population at some point will have heard the information, but that there's an inner equilibrium. And we can model this inner equilibrium or derive it by using differential equations. Won't go into this right now, but the problem is that differential equations, as we've seen, can or have to make some assumptions to be analytically traceable, which are that there is a deterministic process, that we have simple contagions, so we cannot model complex contagions using differential equations, and they assume random networks instead of small world networks. So if we want to know how this looks like in a stochastic process on like close to or exhibiting real world attributes network, then we can use agent-based modeling. And I'm going to show you this. This is now NetLogo, which, as I said, also has a graphical user interface. So what we see here is, again, a network. You cannot see that well, but here it's also the case that one single node is connected to its immediate neighbors and its second-degree neighbors. But we have some overplotting, that's why we cannot see this as well. And at the start, we have 2 people that know this information. Now we're interested in how does this information propagate, and this is the change from before, now there's a 50% chance that people forget. So if they've heard the information, at every time point, there's a 50% chance that they forget this information. If then, of course, someone says, well, or if they then hear the information again, they, of course, know it again and can propagate it again. But in the meantime, they have forgotten. I use the opportunity to present you a little bit how this looks like. So the first slider is the probability of random ties forming. So this is just the network setup. Not that important for our purposes here. Then we have the probability that a transmission is happening. I'm not going to vary this, so this is 1. So if there's a neighbor and they know the information, I will know this information in the next time step. And then there's the forgetting part that I just mentioned. And this threshold parameter here identifies whether it's a simple contagion or a complex contagion. Let's start out with a simple contagion. We can see very fast we achieve somewhat like an equilibrium. So we have some random derivation around an equilibrium. This equilibrium is the analytical equilibrium. So the network structure and the stochasticity does not affect our result from the ODE before, except that it varies around. Let's do like a little, or let's make it more probable that people forget. And there you can see the final size of the diffusion is much slower. It's much lower, and also the start is less steep. So the higher the probability that people forget, the slower the diffusion gets, which makes sense, right? So by now, we can say, well, the network structure maybe changes the dynamics, so it's much faster than we would expect with the differential equation model. But essentially, the conclusions are the same. But now watch what happens if we go to complex contagions. Start out with a lower probability of forgetting. And we already see it's much slower until it gets somewhere. There's a very drastic decrease in diffusion speed. This is so far not so new. This is what Damon Santola already showed. But now with the exception that we still have this inner equilibrium. If the diffusion reaches inner equilibrium, it is again the same equilibrium as in the mathematical model. However, the higher the probability that people forget, there you can see it, the more likely is it that it dies out by random chance. So there seems to be like a critical mass of how many people needs to know it to overcome the random fluctuation. And if the random fluctuation at some point hits 0, it's gone. Compare this to simple contagions again. Here, there's no question about it, immediately skyrockets and surpasses this critical mass. And this is the major insight of this very simple model. I need to go back to my presentation. Which is that, so we already had that complex contagions, which you can see here on the right, are much slower, and they cannot take advantage of the bridging ties. This is what the average path length tells us. So the lower average path lengths, the more bridge ties there are in between. And we can see here that with simple contagions, having like more bridge ties, so therefore shorter path lengths, massively increases speed, whereas in simple contagion it doesn't. And because of this slower speed, there's more time for the stochastic process to reach zero. Therefore, the probability of dying out is much, much higher, that we can see here. So if the simple contagions make it to after the first time step, they immediately have a zero probability of dying out anymore. So if they're not in the first instance go to zero, they will propagate to the equilibrium. But for complex contagions, even after 9 time points, they still have a non-zero probability of dying out. And actually, they have more than 80% probability of dying out within the first few time steps. And this is one additional reason, maybe, of course, need empirical tests for that, why so few behaviors actually spread through a population. They can get trapped in subnetworks, as Santola and Macy showed, or simply they die out because they are so slow. All right. And this is just summary of what I just said. So if the contagion survives, it eventually oscillates around the analytical equilibrium, no matter whether it's a simple or complex contagion. Simple contagions spread very fast, complex contagions spread very slow. And due to their slower speed, complex contagions die out much more likely than simple contagions. And this is, we can think of this as having a critical mass that is sufficiently greater than the standard deviation of the random process. Questions on the first model?
Yeah. How would you decide on the number of nodes you have in your model? Like, is the model sensitive, or how many nodes you decide to have?
It's not. I chose 100 nodes in this case, simply for the reason that you are able to visually see the difference between the nodes. In my original model, they are so closely together that you just see a circle. But in general, you would want to have more, but there's of course decreasing marginal utility in adding more. What the model probably is sensitive to is the number of initially knowing nodes. So again, this critical mass argument, if they transcend this threshold before or at the very start, they will not die out anymore, probably. Jack?
Do you use an approach, like coming from a machine learning background, there's hyperparameter tuning, right? Which is so like a hyperparameter would be, in your model, you've got the percentage chance of forgetting some information, the percentage chance of someone communicating to someone outside their small world. So these are all, and say for example, the population size 100, 200, 1,000, whatever. These are all different hyperparameters, and you come up with every possible combination of all of the different parameters. I mean, you establish some boundaries, right? But you just come up with every possible combination. You chuck them all into your simulation, and then you can kind of see how different hyperparameters sort of affect different outcomes, just to see the sensitivity basically of what different hyperparameters do. Is that something that's done?
Yeah.
Yeah.
For this kind of model, I simulate every possible parameter.
Cool.
And in every possible combination, multiple times.
Nice. Cool.
However, the more complex these models get, the more then it gets not feasible anymore and not useful. But for theoretical insights, it's often very crucial having like edge cases like probability 0 or probability 1 to establish or to get your head around why this is the case.
Yeah.
Why do we observe this?
Okay. Okay.
So that's basically a counterfactual. Is there, if there is something not at all in there, how does it change things? So for simple models, I simulate everything.
Sure, sure. Yeah, we might call that research in machine learning. And then if it gets too big that it's implausible to try really every combination of everything, you can do stochastic operations, which is where you treat it like it's a sample, like our population, and you just try samples to see what the different kinds of effects are. But yeah, no, really cool.
Thank you. Someone else?
Do you explain another example, or like we have to shoot with the questions now? Like the second example comments.
Yeah.
Okay, so can we? Okay.
Yeah, there are 2 more examples coming, but from different research areas. Okay. All right. So my second example, this is more of a theoretical model, concerns the housing market. This is my PhD topic, and I am interested in social and economic segregation in cities, so residential segregation. And we know that there is social and economic segregation to a certain level. And this also correlates with housing quality. So poor people live in lower quality housing. And these inequalities that we observe are all highly correlated and very stable over time. But if there is change, it's relatively fast and usually happens in a relatively small geographic area. So this is so these are stylized tracks of housing markets, of social processes and housing markets. And my aim is to find a unified model for these things, because currently we only have separate theories for segregation, gentrification, neighborhood decay. But I maintain, well, neighborhood decay and gentrification are basically just the dynamics, and segregations are the statics. So they're part of the same complex subsystem, and I try to synthesize these literatures and provide one single model or first draft of some theoretical model. And the basic idea of it is that housing market decisions are economic decisions. So I have preferences of where I want to live, next to whom or something, and I have constraints in regard with prices, and my landlords, of course, are also making economic decisions whether to invest and how much money to charge me. And all of this has spatial constraints. And this is again where agent-based modeling comes into play. It's very hard to model spatial constraints in any other form. Actually, one of the most famous agent-based models from the social sciences is a segregation model, so, by Thomas Schelling. And there are actually some physicists and mathematicians trying to formalize this agent-based model by Schelling, and they are only capable of doing so for a very specific case. So, and the model by Schelling is much, much simpler than my model. So it's very, very hard to model these kinds of interdependencies in any other form than agent-based. So my starting points are, of course, the economic decisions. Therefore, I use microeconomic theory. And there's a model by Stephen Bernard and Rob Willer that is basically a continuous variant of the Schelling model. And what they have done is that they have inhabitants in the cities with 2 characteristics: to their social status and their wealth, which can be said to correlate. And they want to live next to high status others, and the prices for their housing units can either be randomly distributed over the city grid, or they can be influenced by the average wealth of the neighbors in that area. That was the prices endogenous in this model. And what they find is that an interaction of the correlation of wealth and status and price endogeneity produce social and economic residential segregation. to get a feel like how this looks like, I'm going back to that logo to show you this. And maybe we can figure out why this interaction is so relevant. This is how the model looks like. We have a grid that represents the city. In this case, it's actually not a grid, but a torus. So these edges are connected to this edge, the other way around, so that we don't get edge effects. And the dots represent the people living in the city. The larger the dots are, the richer. The brighter the dots are, the higher status. And now we have our two parameters in this model, which is the correlation between wealth and status and the level of price indigeneity. And I set it up to 0.7. Have a look how this looks like. And very fast, we can see real tight clusters, both in terms of wealth and in terms of status. So this is like a status, rich, high status neighborhood. This is deprived areas. Here again. And the higher I increase those, the more extreme these segregation patterns get. And on the converse, we have no correlation at all, or only some minimal correlation. We do not observe these changes. And if I don't have endogeneity but correlation, it's not as clear-cut as it was before. Why is that the case? Why does it make sense? Do you have ideas why price indigeneity and the correlation between wealth and status need to work in unison?
They are trying to connect in like some price, like status, like let's say like price doesn't value the status, but through the correlation it can indirectly vary this like the status as well. I think that's what's going on. Like wealth will go price varies with wealth, but then like people who are like high status, if they are correlated with wealth, that means like they're gonna like move to like, you know, like where they go, the price will go up as well.
Yeah, exactly. So to phrase it in the terms that I from the model here, so people want to live near high status others. Even the poor and low status people want to live near the most high status others. If there is no indigeneity and prices are randomly distributed, people can just go anywhere as long as they can afford to live there. And they don't have an incentive to move or cannot push out of it by price mechanisms if they like the spot. But if we have indigeneity, they can get replaced. There can be displacement via the price mechanism, right? So that's the Bernard-Wille model. What I'm going to do is that I do a similar model with the same household characteristics. The crucial feature is that now the prices and also the attractiveness is not distributed randomly anymore, but I endogenize those. So I have another class of agents, the landlords, that supply housing quality. I have a little bit of a change in the utility function for the residents as well. Now they only have not only have the preferences of I want to live near next to specific social others, but I also value how my flat or something looks like. So the quality of my housing. And so this is just like minimizing some of squares of the social distance. So it's a homophily argument. So I want to live next to people that are socially similar to me, and I want to increase my housing quality. And this parameter then weighs how important are my neighbors, how important is social distance to my neighbors. And then supply landlords then aim to maximize the residents' wealth, but they have an uncertainty problem because landlords cannot know the future development of their neighborhood, but their neighborhood affects how attractive residents think this unit is. So they cannot simply say, well, if I invest this much, I can get people with respective higher incomes, because there's also a social dimension. So they can overcome this uncertainty problem by learning from past experience and or learning from relevant sources. How I implement this is still work in progress. So that's why I've shown you the Benar and Willer model, because there's nothing to show from my side yet. But the idea is basically to have a market model with economic constraints and social constraints. And in the end, this results in a model where the households change each other's budget sets. So they influence how expensive something is and their utilities. So because of social distance, the landlords compete for residents' wealth, and the landlords influence in each other whether to invest or not. We have three types of interactions between landlords and residents and within these categories that I think are characterizing housing market dynamics. And then after model building, I will try to come up with empirical implications of this theoretical model and test it. All right. Questions for the housing market model? You can, of course, always ask me later if you think about something. Then we would go to Oke's example.
Hi, everyone. I'm very happy to have the opportunity to present my research here. I would have liked to present my work on-site in Mannheim, of course. This is not possible, unfortunately. But I would like to thank the team of the M.Sc Social Science Data Lab very much that I can nevertheless present my work in this way. Before I start, I want to say how the model that I present here is different from the models or the examples that you saw before. Before you saw so-called toy model class examples of ABMs. I present here a different type of agent-based model, namely an example how an agent-based model can be used as an in silico laboratory by investigating how specific manipulations, for example, like changing agent behavior in a certain way, influences the quantities of the system. And for this type of agent-based model, the aim is to learn then something about the effect of a corresponding manipulation in the real world. As Malte said before, these models are therefore designed to have a stronger correspondence to the real world, which is why these models are calibrated and validated, as you will see later on. My example focuses on multi-party competition, which is a characterizing feature of politics in democratic societies. Parties compete for votes. Especially, I will focus on multi-party competition, so party competitions with more than two parties. Multi-party competition is a complex and evolving dynamic process. It evolves, it never stops, it never settles at a static equilibrium. And the output of today is the input of the political process of tomorrow. This defines like a complex dynamic system. How to model these multi-party competition. Classical game theoretical models of dynamic multi-party competition are not analytically solvable. This was one reason why Lever and Sargenti in 2011 introduced their agent-based model of dynamic multi-party competition. This builds on earlier work of Lever, and this considers like the dynamic nature of party competition, but it does not only tackle like this analytical problem of classical formal analysis, but it also has some very nice features. It allowed for very realistic behavioral assumptions of parties and voters. For example, parties in this model were boundedly rational and not homogeneous but heterogeneous. So they had heterogeneous attributes. And like a small illustration of this model you can find in the right. Here in the model there are parties that update their ideological positions in certain way, and then voters see these ideological positions of parties and then make their voting decisions in light of these ideological positions of parties. And then parties like see voting decisions, and this informs then their updating of their ideological positions. And this is dynamic and like is ongoing, this process. The work that I will present here builds on this agent-based model, the seminal agent-based model. And the research question that I want to address in this project that I present here is, what are the short-term effects of cordons sanitaires against radical parties on voting behavior in dynamic multi-party competition? What are cordons sanitaires? Cordons sanitaires are erected against some radical parties when the mainstream parties publicly rule out during the campaign that they will not form a coalition government with this radical party or these radical parties. For example, in Germany, like for now, the mainstream parties rule out forming a coalition with the AfD, which would constitute a cordon sanitaire against the AfD. Based on existing research, we have micro-level theoretical knowledge about how cordons sanitaires shape the individual voting decisions. So there are some mechanisms that were tested in survey experiments. So we know how voters like react to these kind of signals, and this literature is. Yeah, or this micro-level theoretical knowledge stems from the literature of pre-electoral coalition signals. You can see like cordons sanitaires can regard it as a specific type of pre-electoral coalition signal. Okay, we have this micro-level theoretical knowledge. However, the implications of this theoretical knowledge on parties' vote shares in dynamic multi-party competitions is not obvious. So it's not clear what kind of effects like this theoretical knowledge has when we really acknowledge the dynamic multi-party or the dynamic nature of multi-party competition. Yeah, in the paper I show in detail why this is not obvious. Here you can believe me. This is not the focus of this talk now. I'm more like focusing on the methodological parts or the methodological like modeling cycle that I went through, not so much on the substantive part. Yeah, but the approach now is to assess the effect of cordons sanitaires by means of systematic what-if thought experiments that I conduct with an agent-based model of dynamic multi-party competition. So the aim is to like infer the logical implications of this existing micro-level theoretical knowledge with the help of an agent-based model. Why do I use an agent-based model for this? There are also other simulation methods. First of all, the agent perspective of agent-based modeling, Malte talked about this before, allows to integrate this micro-level theoretical knowledge about how corridors sanitaires shape individual voting decisions. Yeah, we have explicitly voters and parties in this model, and we can directly like feed in the theoretical knowledge that we have about these two agents regarding the effects of corridors sanitaires. Agent-based modeling, as I said before, acknowledged the inherently dynamic nature of party competition. Agent-based modeling allows to make very realistic behavioral assumptions about parties and voters, bounded rationality, heterogeneity of attributes. And also the approach is very flexible, and this allows me to consider specific characteristics of specific party systems that I want to focus on, or that I want to calibrate the model on. So to repeat again, so this agent-based model here is treated like an in silico laboratory in which the implications of the theoretical knowledge are assessed in a very systematic way. And this is the modeling process that I went through. This is what I want to focus on, not so much on the substantial part of the paper. First of all, you see that I define, or that the researcher in general, when he or she conducts this kind of analysis, has to define the model. So this is model conceptualization. Then in the next step, you should validate this model. So you should argue that this model, how it is designed, has some correspondence to the real world. So in other words, the assumptions are realistic. After that, you or I calibrate the model, the agent-based model, so that the model behavior resembles the behavior of a specific real-world party system that I'm interested in. This is the idea of calibration. So make the model resemble a very specific real-world party system in my case. When this was done, the output has to be validated. So yeah, the model has to prove if it really, when it's calibrated like that really behaves like the real world party system that was used for calibration, or that the model should resemble. In the last step, when the model is calibrated, I can then conduct my thought experiments in this model. So I will now systematically go through these different steps. The first step was model conceptualization. So here I simply now define how the model looks like. So in the model that I take here, of multi-party competition, we have parties and voters that are placed in a two-dimensional ideological space, and this is how the model is set up. So parties and voters are placed somewhere there. Of course, not somewhere. It's later on important and also part of the calibration exercise where to place them. And the dynamics of the model now result from the following 2 points. The parties update their ideological positions according to different heuristics that they have in the light of voter support. And there are 3 different heuristics that I now don't want to elaborate on. You can, these are actually the heuristics that also Labor and Sargenti used. And then the voters indicate their voting intentions in light of the party's ideological positions. And this continues over different time steps until I stop the model. Now, what is different to the model of Labor and Sargenti 2011 is that voters are voting in a coalition-directed fashion, or strategic. They do strategic coalition-directed voting instead of proximity voting, which was assumed by by the original model. I used a collision-directed utility function as shown here. This is nothing that I invented. It's basically the model of Dutch et al. 2011. And the cordon sanitaires now affect the collision expectations. This was like shown in earlier work that this is what collision signals do. And this is the way how cordon sanitaires enter then this model, by changing collision expectations. And yeah, one can simulate this model now with specific cordon sanitaires that change the collision expectations, or without those cordon sanitaires. And this is what I want to do later on, to see how this manipulation of introducing cordon sanitaires changes multi-party competition. After that, yeah, you should conceptually validate the model. So should argue, yeah, the model is like the assumptions are reasonable, and I did this by linking closely to an already existing agent-based model. This is called docking. So I used the model of Lever and Sergenti. And also the model assumptions are in general informed by existing evidence. So I was very careful and not like departing from the literature too drastically. In the next step, I calibrated the model. So I want to find such values for the model inputs that make the model output resemble a very specific party system. I talked about this before. And the interesting case that I want to consider here is the 1930s Weimar Republic. Because in this case, the government takeover by a radical right party, the NSDAP, had devastating implications. And I use this as a setting for my in silico experiments, or I want to use this as a setting for my in silico experiments. As yeah, I can then examine what kind of effect cordon sanitaire would have had on the electoral success of a radical right NSDAP party. Yeah, there was no cordon sanitaire in Weimar because the parties of the political right did not like rule out coalition governments with NSDAP. My aim is to find input values that make the model output look like the Weimar party system of 1930 at time t equal to 0, and like the Weimar party system of 1932 at time t equal to e, which is a model parameter, and this is greater than 0. I used historical data for this calibration. So this is the calibration target data. These are vote shares of the Weimar parties and proxies for historical ideological positions stemming from roll call votes in the German Reichstag. I calibrate this model in a two-step approach. First, some model inputs have directly observable real-world equivalents. For example, the number of relevant parties, which I identified as being 6. There, it's pretty easy to calibrate these inputs. You directly observe them and set them accordingly. But this is not the case for most of the inputs. Most of the inputs don't have observable real-world equivalents. And for those, I conducted a rigorous calibration procedure that itself consisted out of 2 steps. Global sensitivity analysis first, and then approximate Bayesian computation. These are the different model inputs, and as you can see, some of them were calibrated using direct observation. Some of them were identified as not being inferential according to the global sensitivity analysis and therefore fixed. And others are calibrated with approximate Bayesian computation. I will not go too much into the details of this because it would take too much time, but I will want to give you the general idea of that. This is the results of the global sensitivity analysis, using this so-called Sobol method. And the Sobol method indicates the total contribution that each of my inputs has on the variance of the expected model output. And I consider different types of outputs of a model, the positions of parties and the vote shares of parties. And then these Sobol total order sensitivity indices reveal then that there are two non-inferential model inputs, model input E and model input H. These two inputs do not contribute statistically significantly more to the variance of the expected model output than a placebo input that was designed to have no effect on the model output. Here you can see the placebo variable that has by definition no effect on the model. And as there is no difference with between like placebo and E and H, these were not inferential and hence were fixed within their range of theoretical possibility. Concerning approximate Bayesian computation, I calibrated the other inferential inputs with that. I had to define multivariate prior distribution for these inputs. These prior distributions come from like the literature. Some of them were also defined by Lever and Sargenti. Others, there's prior knowledge that I could use for that. Then I drew inputs from this prior, simulated the data for these inputs, and kept those inputs that result in a small difference between simulated and observed data. This is the idea of approximate Bayesian computation. For doing this, I had to define a measure to assess the difference between data observed and simulated. And I had to determine a tolerance level. Yeah, what does this mean? It's a small difference. There I had to define a tolerance level, and for this I used the coverage property. I did a series of robustness checks. I repeated the whole approximate Bayesian computation procedure with more computational power, with slightly different tolerance levels, and with alternative party precision proxies, but the results remained the same. And this is like a picture how the marginal posterior distributions of inputs look like. You see, the uncertainty is large, but this also reflects like the sparse historical data. As a next step, I performed output validation, which is good practice to further increase confidence that there is a correspondence between the model data generating process and the real world data generating process of interest. In my case, the 1930s Weimar Republic. For this, I sampled a set of 1,000 inputs from the approximated posterior distribution. Then I collected the resulting 1,000 predicted values for positions of artificial parties in the election of 1932, which happens at time step 25 in my model. And the results you can see here. As the 80% highest density regions show, the observed party position proxies for the 1932 elections, which are shown in yellow here, yellow points, are likely realizations of the agent-based model. And in the paper, I did some more checks, but this already gives us like confidence there's a certain degree of correspondence. However, you can also see that these predictions are subject to a high degree of uncertainty. For one thing, because of input uncertainty, for another thing, because of random component uncertainty. Input uncertainty would completely disappear if we would have more data, more prior knowledge. So we are very sure about which input values are the right to calibrate it to the 1930s Weimar Republic. However, the second component, the random component uncertainty, would always be there because of the inherent randomness of the system. And later on in the experimentation step, the random component uncertainty doesn't matter because I will calculate expected values. So this kind of uncertainty will be averaged out. But the input uncertainty will be reflected in the uncertainty of the experimental results later on. Now that we have calibrated and validated this model, we can turn to the interesting part, so the in silico experimentation. And here the question was that I wanted to answer: what are the short-term effects of a corridor sanitaire against, in this case now, the NSDAP on electoral success of the artificial NSDAP? And the experimental design of my in silico experimentation is to compare two artificial 1930s Weimar democracies. In one artificial democracy of Weimar in the 1930s, the NSDAP faces a corridor sanitaire, and in the other one, it doesn't. So as a disclaimer or as a reminder, note that it's here, the results that are shown next are systematic what-if thought experiments. So these results reflect the logical theoretical implications of the implemented micro-level knowledge. So the micro-level knowledge that was like fed into the agent-based model. And what we see here is, like in the upper panels, we see distributions for the NSDAP vote shares for different time ticks. This one type of distribution that is shown in brown is the scenario with corridor sanitaire, and the other distribution is shown in gray is the scenario without a corridor sanitaire. And in the bottom panel, you see the first difference. And here you can see that the introduction of a corridor sanitaire against the NSDAP actually increases the NSDAP vote share up to the election of 1932. And it's still significantly, statistically significantly positive at the election of 1932, which is shown here by means of a red line. And after that, the effect is not statistically significantly positive anymore. You also see that the uncertainty is pretty large. As I said before, this is due to the large input uncertainty, but nonetheless, we have here clear direction, namely it's positive and significantly positive. I don't want to get into the details here. As I said, I don't want to talk about the substantive part, but what I did in the paper is then examine the reasons for this. I looked at the individual voting decisions by ideological positions of voters. Here you can see the voters in the two-dimensional ideological space, and there you can see by means of these heat maps the mean predicted probability to vote for the NSDAP. And you can look at this for the scenario with the corridor sanitaire, without the corridor sanitaire, and then you can see the difference between both scenarios. And so this gives me like a reason, or this gives me some indication for why these patterns emerged that we saw in the previous slide. So to conclude, so there are some substantial lessons learned. I could show that under reasonable and mild assumptions, existing theoretical knowledge can predict that a corridor sanitaire against the radical party can actually lead to an increase of electoral support of the radical party in the short term. So this gives an example. So it illustrates the theoretical possibility that these kind of corridor sanitaires can achieve the opposite of what they actually were designed for. And it calls for theoretical and empirical investigations of the conditions under which these strategies of mainstream parties can actually do what they intend, namely reduce radical parties' electoral success. I also learned some methodological lessons. first of all, there's really high computational demand. So for the calibration and in silico experimentation in the paper, I simulated more than 100 gigabytes of data, way more than that. I also would conclude that calibration and also validation of agent-based models is an open and rapidly evolving area of research, not only in political science, where there are not so many attempts to actually calibrate agent-based models, but also in other disciplines like economics. Actually, these calibration methods that I use, like approximate Bayesian computation, are only recently also introduced in economics. But I find that the Sobol method and approximate Bayesian computations are a promising a way to calibrate these models. Another lesson that I learned is that you should really take into account the two sources of uncertainty that I talked about before, namely input uncertainty and random component uncertainty. And input uncertainty is rarely acknowledged. So input values are simply fixed at some values and are not the result of a thorough calibration procedure. I'm happy to have presented you my results of this paper, and I wish you a nice end of the talk and a nice day. Thank you and bye.
All right. That was Oke's example. I'm sorry we're already at the end, but maybe if you have 5 minutes spare, I quickly sum up the conclusions for you. If you have questions later and you have the time to stay around, feel free or write us emails. You know the drill. All right, so to summarize the talk of today, we've given you somewhat of an introduction and some examples of the use of agent-based modeling in social science research, more of like what is it and what can be done instead of like a roadmap of how to do it. And to summarize up, ABMs are computer programs consisting of agents with behavioral rules that are embedded into an environment. These agents are autonomous, they're interdependent, they're adaptive, and often heterogeneous in attributes. The program can then be used to deduce macro-level implications of the behavior of agents at the micro level. ABMs are very flexible, therefore allow for a wide range of research goals. We've identified 4, like from simple thought experiments up to forecasting and experiments. Therefore, ABMs are a tool to model emergence and directly tackle the micro-macro problem that is abundant in social science research. And they allow for a stochastic and dynamic and also networked view on social and political phenomena. Some benefits, we've spoken about them on passing by. So first of all, it's a method to deal with issues that you cannot manipulate experimentally or easily observe. This also relates to the question by on policies. You can relatively easily relax assumptions. With many formal models, we need to have very strict assumptions to get something of a solvable model. With agent-based models, we can be more relaxed about our assumptions. And again, many social science models that we could do mathematically will not have an analytical solution. And there we need numerical simulations again, even though you're using, for example, differential equations. Our hopes and likely future developments, so our personal take from the current state of agent-based modeling in the social sciences. First of all, calibration will likely gain much more importance and methodological attention. We talked about prediction and the evaluation of policies before. This will be likely something that we'll also see more in the social sciences, which is quite common in some other sciences already. And agent-based models might also be a framework that we can use to achieve more theoretical synthesis, hopefully, in the social sciences and to compare and unify existing theories of social phenomena. If you're intrigued by our talk and want to learn more or more specifics, we have some recommended literature for you. First one is a review from Sociology, quite old already, but a very nice introduction and gives some overview over some substantial fields that use agent-based models. And there's a more recent one in the annual review of political science, although they do not review substantial progress derived by ABMs. More recent one that does so is the chapter by Flacher and Macy in the Oxford Handbook of Analytical Sociology. If you want to know more on how to implement an agent-based model and the steps necessary, there is a Sage book, it's like the little green book in the applications in quantitative social science or quantitative applications in social science series by Nigel Gilbert. Very recent, second edition, updated version. Highly recommend. If you're interested in using agent-based models with empirical research and how to connect them to empirical data, there's a piece by Brooke and Atwell in Sociological Methods and Research. And so there's the original model that Oke talked about by Leve and Sargenti. And if you're interested in this idea of the micro-macro problem and how we can tackle this, I recommend you to read Scott Page's article, What Sociologists Should Know About Complexity. All right, thank you so much. 5 minutes overdue, but I hope you excuse us, and thank you so much for your attention.
Thank you so much, Malte. Thanks to both you and Oke for this very instructive and inspiring talk today. Thank all of you online and in this room today for your participation. And the Social Science Data Lab will be back in 3 weeks on December 7th for the final session of fall 2022, when Teresa Gessler is going to talk about her work on group political text. Thank you all, and we hope to see you soon.